Today we're going to do the synthesis of T-butyl chloride. So this is our first reaction experiment that we're going to do. So when I give all of these reaction experiments, most of them from now on will be reaction experiments, I'm going to give you the mechanism. And this is how I'm going to give it to you. I'm going to show you that our T-butyl alcohol is going to attack the hydrochloric acid, so the electron pair on the O goes to the positive H on the hydrochloric acid, and that HCl bond is broken going to the Cl. And you always put your electron pairs whenever you're doing your mechanisms. And so we now have put an extra H on the O, which is a water group that is then going to leave. And so I have the arrow, double-headed arrow, both electrons going to the O, and that leaves us with a carbocation. So a T-butyl carbocation, so a tertiary carbocation is a stable carbocation, which is then going to be attacked by a negative chloride ion. So the electron pair on the chloride ion attacks the positive carbon to give us our T-butyl chloride. All right, and so you will have to write the mechanism in the lab book, and if you write it like this, it is wrong. All right, if it was on an exam and it said mechanism, that would be fine. In lab, the mechanism in the lab book, all reactions must be balanced. You must show all lone pairs and all formal charges. If you do not show them, you will lose points. And then you must also show the overall reaction. All right? And so here is how you will have to convert the given mechanism into the correct way to put it in your lab notebook. All right? First step is the same. Our T-butyl alcohol attacked the HCl. That looks exactly the same, except it says step 1 of the mechanism. It's going to be a balanced chemical reaction. And so we have our same product that we had before, the T-butyl group along with our water attached to it, but you also show that that has a Cl minus, so that step is balanced. Now you go to the second step, so step 2. Now we are going to have the water leave, and so the bond from that carbon oxygen is then broken, as shown there. All right, and then you get your tertiary butyl cation, so the T-butyl cation. All right, but you also have water, so you show the water because it is then now a step 2 that is a balanced chemical reaction. All right, and then in step 3, you have your carbocation, the T-butyl carbocation, reacting with the Cl minus to form your T-butyl chloride product. All right, so then when you add up the 3 steps of this mechanism, I will show it now, that your when you form this complex, all right, so this was formed, and then we used it in a subsequent step, this one, and so this is a reaction intermediate. All right, and so when you make something and then you use it up, it is a reaction intermediate. There is another reaction intermediate, and that is your tertiary butyl cation, and so that also is gone. All right, and what you also see is that the Cl minus is also a reaction intermediate. It was formed in step 1, and we used it up in step 3. All right, and so when you subtract your ions on both sides, you see that you're only left with the step 1 reactants. All the other reactants, the reactants of step 2, reactants of step 3, they canceled out. All right, but we have none of the products of step 1. Both of them have canceled out. In step 2, water is left, and that's why water is a product. And then, of course, your final product, the T-butyl chloride, is the other. All right, and so you show that your reaction intermediates are going to cancel out. Had we added something and then used it and got it back in a subsequent step, that would then be a catalyst. All right, if you make it and use it up, it's a reaction intermediate. It does not show up in the overall reaction. If you added a catalyst and it doesn't show up in the overall reaction because a catalyst also cancels out, but a catalyst is added and then it is made, and that's how it gets canceled out, a catalyst is always going to be put above the arrow. All right, so given that this is our first synthesis reaction, I'm going to do also the calculation for limiting reagent, theoretical yield, and the percent yield. So you have to take each reactant. So you look at the reactants in your overall reaction, and you have to then use those. And as we read our instructions, we're going to use 6 milliliters of our T-butyl alcohol. All right, and so this is the symbol for T-butyl alcohol. You look up the density. The density is 0.781 grams per milliliter. And so, again, you should show that your units are going to cancel. So I put the milliliters on bottom so they cancel the milliliters on top. So now I have grams of T-butyl alcohol, and then I look at the periodic table and find the molar mass. And so my grams of T-butyl alcohol will cancel with my grams of T-butyl alcohol from my density. And so now I have moles of T-butyl alcohol. Then from my overall balanced chemical reaction, everything here is 1-to-1 molar ratio. And so I have 1 mole of T-butyl chloride is made from 1 mole of T-butyl alcohol. So my T-butyl alcohol, moles of T-butyl alcohol will cancel. And then I have the molar mass of my T-butyl chloride, which is 92.57. And so again, my moles of T-butyl chloride will cancel my moles of T-butyl chloride. And then when I push all the buttons, everything on top you multiply, everything on bottom you divide, and you get to the correct number of sig figs. We're only going to use 6.0 milliliters. So 2 sig figs, 5.9 grams of T-butyl chloride. All right. So then you have to do the same thing with your other reactant. Now, if you have an organic reactant and an inorganic reactant, your organic reactant is 99% chance that that's going to be your limiting reagent. But you still have to show that the HCl is not your limiting reagent. So in this experiment, it says use 17.5 mils of concentrated hydrochloric acid. All right, and so concentrated hydrochloric acid is 12 molar, or 12.0 moles per liter. And so you take your 17.5 milliliters of HCl, and then you just convert it to liters by dividing it by 1,000. So now we have liters of hydrochloric acid as the milliliters cancel. And now you can multiply that by the molarity of your concentrated HCl, which is 12 moles per liter. And now your liters cancel, and you have moles of hydrochloric acid. Again, everything in overall reaction had a 1-to-1 mole ratio. So 1 mole of HCl produced 1 mole of T-butyl chloride. Moles of HCl cancel. And we have the same molar mass. So T-butyl chloride's molar mass, 92.57 grams per mole. Moles of T-butyl chloride cancel moles T-butyl chloride. And so now you have the mass of your T-butyl chloride that can be produced from 17.5 mils of HCl. And that is 19.4 grams of T-butyl chloride. And so your theoretical yield is the lower amount. Always the lowest amount formed is your theoretical yield. So if you had everything work out perfectly, you would have 5.9 grams of T-butyl chloride. That is the theoretical yield. All right, and so then that came from the T-butyl alcohol, which makes the T-butyl alcohol the limiting reagent. All right, and so to find the percent yield, we can't do that right now, because to find the percent yield, you're going to take your actual yield in grams, we're going to weigh it in grams, and divide by the theoretical yield, which is the 5.9 grams, and multiply by 100, and then we will have our percent yield. And you will have to do that for every reaction that we do in organic lab. All right, so now we're ready to get started on the experiment. All right, looks good. All right, so the directions. Synthesis of T-butyl chloride. There's only 7 steps. Hopefully it doesn't take too long. In a separatory funnel, right here in our separatory funnel. We used it last time for the extraction. We're going to run our reaction. So the stopcock is closed so it doesn't go right through when you add your liquids. All right, I have my ice-cooled 17.5 mils of concentrated hydrochloric acid. All right, so we're going to put that in our separatory funnel. All right. All right, so that was 17.5 mils of concentrated hydrochloric acid. That was cooled to 5 degrees Celsius. And now we're going to add 6 mils of T-butyl alcohol, and we're going to do the reaction right here. So here is my 6 mils of T-butyl alcohol that I measured out. And so you can see there, well, I don't know if you can see, but well, it looked like it was 2 layers, but it could have just been the hydrochloric acid being so cold that it made it a frosted glass. Again, we will vent. Since we made the hydrochloric acid so cold, it's going to react slower. You're not going to hear any swishing noise, and we're not using a volatile organic solvent. There's no ether or any alcohol, but there is a reaction going on, and this reaction is exothermic, and we're also warming up our cold hydrochloric acid, and so that is releasing some pressure as well. So as it is heating up, it's going to build up pressure. Okay. This way. Don't want to reach across so you can hear it. I'm getting a little more vigorous with my shaking. And you might be able to hear the rain that's coming down outside. And it says to react this for about 20 minutes. And we're going to get 2 layers, because what I didn't explain in our mechanism over there, that our alcohol is OH, and then that's very polar, it's got hydrogen bonding, and so it is going to be miscible, it's going to mix freely with our acid, aqueous acid. But now we're making T-butyl chloride, and so there's no hydrogen bonding. And so now it is an organic that is a relatively non-polar organic. It is not going to be soluble in water. And so we're going to end up with 2 layers. So we only saw 1 layer. It looked like it was going to be 2 layers, but it was a fog layer. All right, but now when we put this down, and now I'm not getting any kind of release of pressure, and so I'm just shaking it up. No release of pressure, and so it's pretty much done reacting. And so when we let it set here, we're going to see 2 layers. We're going to have our organic layer is going to be on top with the 1 chlorine. If it was going to be a dichloro compound, then that would be heavier than the aqueous, and it would be at the bottom. If you are not sure, you can do the 1 drop of water test, and you can add the drop of water. If it immediately disappears, then that's your water level at the top. If you see it go through and disappear into the bottom layer, well, then you saw the water go through the organic layer and into the aqueous layer and then disappear. And so you now know that the aqueous layers on the bottom, your organic layers on top. All right. All right, so while this is separating, it takes a while to separate, I'm going to set up a distillation. So we're getting a liquid here, and so we're going to have to purify it by doing a distillation. And so you can watch the setup of a distillation. And you can say, I'm glad I'm not doing that, I'm just watching that. Okay. All right. So to do a distillation, you need 3 ring stands. And we're going to need a heat source that we will use. I prefer a Bunsen burner. Some people prefer hot plates. I prefer a Bunsen burner always. All right. And now the amount of liquid that we're going to get is a very, very small amount. Our theoretical yield is 5 grams. So we're going to use the smallest container for this distillation that is in our box over here. And for this box, looks like we're missing our 25, so we're going to have to go with the smallest one in there, which is a 50 ml round bottom flask. All right, so then our adapter, the first adapter that goes in looks like this. The thermometer is going to go in here, and that's going to go to our condenser. Again, there's a picture of this on Moodle. And we need our condenser. All right, condenser already has the hoses on it. All right, and so when we hook up our condenser, we have to clamp everything to make sure that it will not fall. So we'll hook up this clamp here, and then we can adjust it onto our raise it, lower it, wherever we need it to go in order for this to make a good connection. A little bit. All right. Looks pretty good. And then this is what we will then collect it in. And it's got a air hole here that it will not build up pressure. It will be released. And let's see, are we gonna there? All right, so I'm just going to secure this in case it falls out for some reason. It shouldn't, but it might. And so this will then catch it. So if that happens to fall, it will catch it. Now, I wanted to collect it in this beaker here. Now again, I don't want the vapors to escape, and so what I'm going to do is I'm going to take my ice cool bath here. I'm going to get some more ice. Less water. Alright, okay. I'm going to collect it, actually, in an Erlenmeyer flask. So I have weighed my Erlenmeyer flask, and so I can collect it in my Erlenmeyer flask. I want the Erlenmeyer flask to be cold, so I'm going to put it in some ice water. That up quite a bit, so not that much ice. What I need to do is I need to put the ice in afterwards, so I'm going to pour that out, put the ice around the sides of it. So now I have it ice cooled. I want to make sure that when the liquid comes in that it cools down and it doesn't evaporate out. It stays in the flask. And I don't want the drip to be very far. I want that to go in. So I have to lower this whole apparatus here. Alright, so I need to lower the whole thing. So this side has to be lowered. And then the middle has to be lowered. And then this has to be lowered. So it takes some engineering to get this to be at the exact level that you're looking for. All right, down some more. And it's all clamped. It's not going to go anywhere. Do not force it. You will. It is glass. It will break if you force it. I'm just bringing it down slowly. Bringing it down slowly. All right, so now I have this that's dripping in there. It's going to go into that flask, and that's all I'm looking for. It's going into that flask. All right, so then I have to make sure that all of my joints are nice and tight. All right, and then now I'm ready to hook it up to the water. Now again, the water is going to go in the bottom so that it then fills up the entire condenser, and then it goes out the top. If you go in the top and out the bottom, it's just going to have water at the bottom and that's it. So you want to go in the bottom, out the top. And when you turn on this water, it doesn't need to be going very fast. Alright, so that's good. Just have water going through. Does not need to be flying through there. And you can check the other side coming out, and that is plenty, if not too much water coming out. Alright, and alright, we got to set up our thermometer so that we can get the boiling point. So again, when we have a liquid, we're going to get a boiling point to determine if we have the correct product. Wipe this off, looks a little dirty. All right. All right, good. All right, so now once we are ready to start, we can just put our liquid in there and then we can start our distillation. All right, let's see how our separating is going. So again, we're only talking a few milliliters of product that we're going to get here. All right, so probably can't, I can barely see it, but the top layer is a clear liquid versus the bottom layer is a cloudy layer. All right. So we do have the two layers, and let's see, I'll lower this down. I'm going to collect that in that beaker there. So again, the top has to be off of your separatory funnel, because if you don't and you try to get the liquid out, it's like having your finger on top of a straw. It's not going to let it out. All right, so we're going to separate these two layers. So as it comes down, there's less volume. You might be able to see it in the video, you might not, but that clear layer is going to be getting bigger and bigger because the volume that is taking up is the same, except down here it's a smaller diameter, and so it's going to then look like a larger amount. right, and then when the cloudy part gets down to the bottom, close the stopcock. All right, so now it says to wash it. Where are my directions? Okay. All right, so you wash it with 10 mils of water. All right, so we have our deionized water. You have your graduated cylinder. And it really doesn't matter. I'll measure it, but there is no need to measure it. All right, so 10 mils, it doesn't matter. It's just washing the product. All right, so it was hydrochloric acid was our reactant, and we had excess hydrochloric acid. All right, so we're going to wash it. We're going to just dilute the hydrochloric acid. If there's any remaining, it should have all been taken out of this step. But we are going to wash our product. I'm going to grab another beaker and drain it into another beaker. Now all these washings can go into the same container. All right, so we'll want to mix it up. All right, so again, gently the first time, and you get the release of pressure. All right, and so we'll let that separate. Again, top off so that we can easily remove the liquid from the bottom. So the next time we're going to use 5% sodium bicarbonate, so it's just baking soda, 5 grams of the solid baking soda into 100 grams or 100 mils then of water mixed up. That is how you make a 5% sodium bicarbonate. Chemistry will do a mass percentage almost exclusively, unless you're talking about an alcohol percentage, which would then be a aqueous percentage. All right, so we're ready to separate these two layers. And then we add our sodium bicarbonate. If there is acid, this will release carbon dioxide, so you may see some foaming. If there is acid in here, the sodium bicarbonate is going to react with it, releasing CO2 gas. If there was any, it was very, very, very minimal. I did not see any formation of carbon dioxide. All right, so again, we'll mix this up. You can hear the release of pressure. And again. All right, I meant to switch my hands. All right, and that didn't work. All right. May have lost a little product there. That's all right. We're not worried about our yield. Just making sure we get some. All right. All right, so then we let that separate. Now, every time you wash your product, you're going to lose some of your product, but we want it to be as pure as possible. All right, so then one more washing with 10 mils of water. And we're not making very much. Again, we're making 5 grams. In this reaction, we could be making a lot more and it would be fine, but again, we're not worried about yield, and so we are worried about how pure is our compound going to be. All right, so this is the last washing with water. Get this lined up correctly. All right, so it's lined up correctly. And this is how you wash a liquid. All right, and so that is our final washing. Once we separate this, we're going to then dry it. Right. And so now we got to get a drying agent, and we're going to use calcium chloride. All right, so I stored my calcium chloride in a desiccator to make sure that it stayed dry and not reacting with the air. All right, and so we have calcium chloride, which is a white solid that is going to absorb, it's going to take in all of the water. So when it says to dry this liquid, we're not waiting for it to evaporate. We are just putting it on so any liquid that's water in here would have mixed with our product. Even if we went out the top, we would have had some issues. All right, but I went out the bottom because I wanted some water to get through, and in this solid, a couple of those chunks are now clumped together, and you know that they have taken in some of that water, so we know it is working. All right, you don't see anything, you don't feel anything. It might be a little warm, but there shouldn't be that much water to make it warm. So it's a very small amount of water. You can't see anything happening here, but what's happening is any water is going to be absorbed through this liquid. Calcium chloride is a dihydrate. So this is CaCl2 without water, anhydrous, and then when it reacts with water, it forms CaCl2.2H2O. And so it takes in all of that water, and we added a gram of calcium chloride, which will take in a lot more water than we should ever have in our product. All right, so now we're going to decant into our distilling flask. All right, so it's going to stay there. All right, and before we start, I'm going to get I'm going to weigh it before and after. I know distillation with this amount is going to lose a lot of product, so I'm going to get a crude yield. So this I'm going to be considering as my yield of the product, and I'm doing this distillation, I'm going to purify it. Alright, so the mass of our product is 1.6 4 grams, 1.64 grams. All right, and then, so this distillation is going to get us our boiling point more than anything else. All right, it will purify our liquid as well. We did a lot of washings, we did drying. This is a high purity, and if we had our NMR up and going, we could take the NMR and see if there's impurities in it. All right, but we are ready to go here with our distillation. I will turn on the gas. And let's check one more thing. All right, so we are ready to start our distillation. So we'll light the Bunsen burner, turn on the gas here, got it closed here. Okay, air holes are opened. Start, turn this down a little bit. And again, you can hold the Bunsen burner, it's not going to get hot. So I didn't put any boiling chips in there because the liquid is such a small amount of liquid that this is really just going to get me the boiling point of my T-butyl chloride. So it is boiling. I'm looking at the solvent front. All right, now it's on the thermometer, and I'm getting a boiling point. Right now it's at 50.0. So the boiling point, 50.0. And so good thing we waited before, because our volume that we had, and there's a couple of drips coming over, it's going to be a couple of drips, which again, when you have your NMR, would be nice. Then you would have your pure T-butyl chloride to test. You get a nice IR, a nice NMR. NMR, you hardly need any product at all to get a good NMR. So the good point is, it didn't take long to do the distillation. And the bad part is, we have very, very small amount. So we've had probably 10 to 15 drops. I don't know if you can see it coming through, but it is still coming through. And it is drawn to the cold, so this is hot over here, and so the vapors are coming over here, and they're cooling off here, turning into liquid, and then they're going to go into my ice-cooled flask where they will stay a liquid. And so a 50 degrees, 50.0 was the boiling point, so you'll have to check the boiling point for T-butyl chloride to see if that is the correct boiling point. Also check that against T-butyl alcohol to make sure that we just didn't have unreacted T-butyl alcohol. We know that's not the case because T-butyl alcohol mixes with water. This was a separate layer. All right, we could have gone with larger volumes. We could have done this at a slower pace. We could have gotten a higher yield. But again, this is how you would make T-butyl chloride. You would take your T-butyl alcohol, react it with your concentrated hydrochloric acid. All right, and so then to remove this, anything inside of here. So we will remove our clamp here, which will allow us to product. We don't want this to fall off, so we'll put this back in place to hold. If it happens to release here, it will hold it there. All right, and so now hard to say what the product is compared to the water on the outside, but we have product in there. And if we wanted to weigh our product after distillation, so the product after distillation only weighs 0.66 grams. And so the 1.64 grams is what we're going to use for our actual yield. And that is the end of the synthesis of T-butyl chloride.